Howdy. This video is on phase transitions and phase diagrams. Phase transitions are very common in important chemical processes. Phase diagrams indicate which phase is the most stable under different conditions. After watching this video, you should be able to describe how temperature is just a measure of kinetic energy at the atomic level. You should be able to describe the relationship between intermolecular forces and phase transitions. You should be able to describe the relationship between vapor pressure and boiling point. And so we'll see that when the vapor pressure is equal to the external pressure, then the liquid boils. You should be able to describe how vapor pressure changes as a function of temperature, and you should be able to describe phase diagrams. And so in a solid, the intermolecular forces are strong enough that it restrains the motion of the particles. And so you'll see vibrations in solids, but you won't see a lot of translational motion of the particles. In liquids, intermolecular forces are strong enough to keep the molecules in close proximity, though the molecules are able to move relative to one another. And in gases, intermolecular forces are typically negligible. And so you can think about it as a continuum. On the far left, you have intermolecular forces very important, and kinetic energy is only seen in terms of the vibrations. On the far right, motion is important. Intermolecular forces are negligible for a gas. And so there's always motion at the atomic level, even for solids, even at 0 Kelvin. 0 Kelvin just means that the lowest energy state is filled, but you'll still have vibrational motion. And so phase transitions can be thought about in terms of competition between kinetic energy and intermolecular forces. And so when you go from a solid to a liquid, you're adding kinetic energy, and so the particles can overcome some of the intermolecular forces. Going from a liquid to a gas, you heat it, add more kinetic energy, and so the particles can completely overcome intermolecular forces. And so there's always motion at the atomic level. This is a decent simulation of ice at 0 Kelvin. The time bar represents 1 picosecond. That's 10 to the minus 12 seconds. And so you see the motion is very, very fast. Ice has a very open structure because that optimizes the hydrogen bonding between the water molecules. Now, if we heat this, what's going to happen is the particles are going to move faster and partially overcome the intermolecular forces. And so solids melt when the kinetic energy is able to partially overcome intermolecular forces, and the particles can move relative to one another. Now, likewise, if we take the liquid and we cool it down, removing some kinetic energy, remember temperature is just a measure of kinetic energy at the atomic level. And so if we lower the temperature, then the particles have less kinetic energy, and intermolecular forces dominate, and we go from a liquid to a solid. And so this is a decent simulation of ice melting. We start with that nice open structure for ice. As we heat it, we're adding kinetic energy to the particles, and then the molecules eventually partially overcome intermolecular forces, and we get to liquid. And so the stronger the intermolecular force is, typically the higher the melting point. Not always, but typically. Likewise, if we go from a liquid to gas, if we heat the liquid, we're adding kinetic energy to the particles, and eventually the particles can overcome intermolecular forces, and we get the gas. Now, if we take any gas and we cool it, it will condense. And so cooling it, we're reducing kinetic energy, and eventually intermolecular forces will become very important and will form the liquid. Now, it's kind of interesting. Whenever you have a liquid, some of the liquid molecules will escape from the liquid into the gas phase, and you will have a vapor and a vapor pressure. And so a way of thinking about it is, say we put some liquid in a sealed container. Some of the molecules will escape, go into the gas phase, and eventually we'll reach equilibrium, where the rate of the molecules going into the gas phase is equal to the rate of the molecules going back into liquid. And so all liquids will have a vapor pressure. Now, the stronger the intermolecular forces, the stronger the traction, the more stable the liquid is, and the fewer molecules will escape, and the lower the vapor pressure. And so please remember, stronger intermolecular forces, higher the boiling point, lower the vapor pressure.
In a closed container, molecules move back and forth between the liquid and gas phases. If the rates of crossover are equivalent, the overall amount of substance in each phase remains constant. The system is said to be in a state of dynamic equilibrium.
it's also kind of interesting that the amount of liquid doesn't affect the vapor pressure. And so if we have a lot of liquid, we'll have a vapor pressure. If we reduce it and have a very little liquid, we'll still have exactly the same vapor pressure. And so all liquids will have a vapor pressure, even mercury. And so you can actually see mercury vapors if you put the mercury between an ultraviolet light source and a fluorescent screen. And you see that slight dark cloud going to the right, and that's actually the mercury vapor. And so many years ago, there would be mercury thermometers in schools, and occasionally they would break, and then you get mercury fall on the floor, someone gets stuck in the cracks in the floor, and then you'd have mercury vapor in the school, and mercury is very toxic. And so there no longer are mercury thermometers in schools. But I mentioned that the vapor pressure is independent of the amount of liquid. And so butane has weak intermolecular forces, only London dispersion, and so it has a relatively high vapor pressure of over 2 atmospheres. And so if your butane lighter is full, your butane will have a vapor pressure over 2 atmospheres. As the butane lighter gets less, you'll still have a vapor pressure of over 2 atmospheres.
The liquid in the butane lighter is in dynamic equilibrium with the gaseous butane, which has a vapor pressure of about 2.4 atmospheres. When the valve is opened, butane gas escapes from the lighter, the system goes out of equilibrium, and liquid butane rapidly evaporates into the gas phase. When the valve is closed, the system quickly comes to equilibrium again, with the pressure of the butane vapor equal to 2.4 atmospheres.
So vapor pressure is independent of how much liquid you got. And again, the weaker intermolecular forces, the higher the vapor pressure because it's easier for the molecules to escape the liquid. The stronger the intermolecular forces, the lower the vapor pressure because it's harder for the molecules to escape into liquid. Also, the stronger intermolecular forces, the more stable the liquid is. Now, I've mentioned that temperature is a measure of kinetic energy at the atomic level. And so you can actually plot the kinetic energy for different temperatures. And so this blue line represents the kinetic energy for a series of particles at low temperature. And then as you raise the temperature, what happens is the average kinetic energy increases, goes to the right. Also notice that the distribution gets a little bit broader. Now, if you imagine that there's a minimum kinetic energy needed to escape from the liquid to the gas, and that's represented by the dashed line here. We see that the higher the temperature, a larger fraction of the molecules are able to escape into the gas phase. And so what this tells us is that as we increase the temperature, the vapor pressure should increase because as we increase the temperature, a larger percent of the particles can leave the liquid and go into the gas phase. And so here's a plot of vapor pressure as a function of temperature for diethyl ether, ethyl alcohol, and water. And so of the compounds on the graph, which must have the weakest intermolecular forces. And so if we look at one temperature, and so say here, notice that the diethyl ether has the highest vapor pressure, then the ethyl alcohol, and then the water. And so that tells us that the diethyl ether must have the weakest intermolecular forces. The weaker intermolecular forces, the higher the vapor pressure at any given temperature. Now, a liquid boils when its vapor pressure is equal to the external pressure, or if it's an open container, the atmospheric pressure. And so the line here on the graph represents atmospheric pressure. And so that tells us that the diethyl ether should boil at 34.6 degrees. The ethyl alcohol should boil at 78.3 degrees. And the water boils at 100 degrees Celsius. And so again, a liquid boils when its vapor pressure is equal to the external pressure. And so the compounds on the graph, which must have the lowest boiling point, and that would have to be the diethyl ether. And so the stronger intermolecular attraction, the more kinetic energy is needed to overcome the intermolecular attraction. Typically, the higher the melting point, the higher the boiling point, and the lower the vapor pressure at any given temperature. So again, as we increase the temperature, we're increasing the vapor pressure, and the liquid will boil once the vapor pressure is equal to the external pressure.
As heat is added to a beaker of water, the vapor pressure of the water increases, thereby increasing the rate of evaporation. If enough heat is added, the vapor pressure of the water equals the atmospheric pressure. At this point, large bubbles of vapor begin to form in the liquid, and the liquid boils.
And so we can cause a phase transition just by heating. Now we can also cause a phase transition by changing the pressure. And so for the beaker, it's open to atmosphere, and so the external pressure is just atmospheric pressure. Now we've put water in a sealed container, and if we reduce the external pressure in the sealed container, then we can also cause the water to boil.
In the flask is water heated to about 55 degrees Celsius, well below water's normal boiling point. We use a device to evacuate the air from the flask. The water boils, though its temperature remains at around 55 degrees.
Now, if you climb a mountain, the pressure on the mountain, the atmospheric pressure is much lower. And so at sea level, the atmospheric pressure is about 760 torrs. Now, if you climb Mount Everest, the atmospheric pressure is 240 torr. And so the boiling point at sea level is about 100 degrees Celsius. The boiling point on top of Everest would be 70 degrees Celsius. And so a phase diagram shows you what is the most stable phase, okay? So again, most stable phase. Remember, all liquids have a vapor pressure. And so in this green region, you're going to have both liquid and vapor, but the liquid is the most stable phase.
Phase diagram specifies the physical state of a substance as temperature and pressure varies. The diagram consists of regions separated by lines. Each region displays the conditions at which a particular phase is stable. Each line between two regions displays the conditions at which those two phases are in equilibrium. This phase diagram is typical for most substances. In general, lower temperatures and higher pressures correspond to the solid phase. Higher P and T correspond to the liquid phase, and lower P and higher T correspond to the gas phase. Let's take a closer look at the diagram and view the various parts on the molecular level. A magnified view within the solid region shows the regular array of tightly packed particles typical of a crystalline solid. Note that the particles in a solid are not fixed, but jiggle in place about their crystal sites. A magnified view of the liquid reveals a major difference between it and the solid. The particles are still in close contact, but their positions are much less restricted than in the solid, and they roll and tumble around one another. In stark contrast to the solid and liquid phases, a magnified view of the gas shows the particles far apart, except when they collide.
And so again, the different regions tell you what is the most stable phase. And so again, here in the green region, you'll have liquid. Liquid is the most stable phase, but you also will have gas because all liquids have a vapor pressure. Now, higher temperature prefers the gas. So as you heat something, it will become a gas if it doesn't decompose. High pressure favors the phase with the highest density. And so if we look at this phase diagram, you notice that if we started here and we go up in pressure, we're going from the liquid to the solid. And so for the compound represented by this phase diagram, the solid is more dense than liquid, which is typical. Now, if we look at water, we see that the line between the liquid and the solid actually slopes to the left. And so if we go up here and go straight up, we can go from a solid to a liquid. And so that tells us that for water, the liquid is more dense than the solid, which is very unique. I don't know of any other compound where the liquid is more dense than the solid other than water. For CO2, if we go straight up, we go from liquid to the solid, meaning the solid is more dense, which is typical. Typically, the solid is going to be more dense than the liquid. But for water, the liquid's more dense than the solid because, again, solid has that open structure to maximize the hydrogen bonding. And so we can cause a phase transition by changing temperature or pressure, or by changing both.
Happen to the sample if we steadily increase the temperature at constant pressure. That is, move horizontally from left to right on the diagram. The changes depend somewhat on the starting pressure. Let's begin at some pressure between the critical point and the triple point. Starting with the solid, we increase the temperature until the solid and liquid are in equilibrium. Increase the temperature above the melting point, and pure liquid exists. Then, the liquid and gas are in equilibrium, and further heating vaporizes the sample to the gas. Suppose we had begun at some pressure below the triple point pressure. We begin with the solid as before, but heating brings the solid into equilibrium with the gas, not with the liquid. And further heating sublimes the solid to the gas. Carbon dioxide behaves this way. It has a triple point pressure of 5.1 atmospheres. Warming a piece of dry ice at ordinary room pressures of around 1 atmosphere changes it directly into the gas. Liquid CO2 is not stable at 1 atmosphere.
And so if you heat below the triple point, you can go from the solid to the gas, which is called sublimation. CO2 is an example where the triple point pressure is much higher than atmospheric pressure, and so CO2 solid will sublime at atmospheric pressure. Now, if you take ice, water ice, and you lower its pressure and then you heat it, you can even get water ice to also sublime. You just have to be below that triple point. And so you can cause phase transitions by changing temperature, changing the pressure, or both.
See the changes the sample undergoes as we decrease the pressure at constant temperature. That is, move down the phase diagram. Here, the starting temperature determines how the sample changes. If we start with the solid at some temperature higher than the triple point temperature and lower the pressure, we first reach the solid-liquid equilibrium state. Thus, the sample melts due only to a change in pressure. Then, the pure liquid exists until a further pressure decrease balances liquid and gas in equilibrium. And finally, the pure gas. Notice that if we start at any temperature lower than, to the left of, the triple point temperature, we move directly from solid to gas. Here's the phase diagram showing all the regions, points, and equilibrium processes.
And so, again, each region tells you what is the most stable phase. The lines indicate that the two phases are equally stable. And so this line says that on this line, the liquid and the gas are equally stable, have the same energy. On this line, the solid and the liquid have the same energy. And on this line, the solid and the gas are equally stable and have the same energy.
At any point along the solid-liquid line, the phases are in equilibrium. Melting and freezing are occurring at the same rate. In other words, the same number of particles are moving from the solid to the liquid per unit time as are moving from the liquid to the solid. Similarly, At any point along the liquid-gas line, vaporizing and condensing are occurring at the same rate, which means that the number of particles moving from the liquid to the gas per unit time equals the number moving from the gas to the liquid. Finally, along the solid gas line, subliming and depositing are occurring at the same rate. That is, the same number of particles are moving from the solid to the gas per unit time as are moving from the gas to the solid. Two other features of the phase diagram are important. The first is that the liquid gas line ends at a point called the critical point, beyond which the distinction between a liquid and a gas disappears. Let's close in on this point and 2 points very close by to see what this means. At a nearby point in the gas region, the gas is under very high pressure, so the particles are reasonably close to each other. Thus, the density of the gas is relatively high. At a nearby point in the liquid region, the liquid is at a very high temperature, so the particles are beginning to separate from each other. Thus, the density of the liquid is relatively low. As these 2 points approach the critical point, the particles in the gas move even closer together and the density increases, while the particles in the liquid separate even more and the density decreases. At the critical point, the densities become equal and the phase separation between liquid and gas disappears. The second important feature occurs at the junction of the 3 phase boundary lines. At this point, called the triple point, the 3 phases are in equilibrium simultaneously.
And so the movie did get the lines wrong. And so the movie was saying that the lines mean that the system's at equilibrium. Has nothing to do with equilibrium. The line means that the 2 phases have the same energy. You can have equilibrium at any place on the phase diagram. If you're right here, you can have a system that is at equilibrium, which means that you're going from one thing to another thing the same rate, that the concentrations are fairly static. And so the lines do not mean equilibrium. The lines do mean that 2 phases have the same energy. The critical point is really kind of cool. And so this line between liquid and gas just stops. And it stops at what we refer to as the critical point. Past the critical point, you can no longer distinguish between the gas and the liquid. And you have what's referred to as a supercritical fluid. The triple point just means that 3 phases have the same potential energy. And so in this diagram, you have a solid, liquid, and gas phase. They have the same energy, and that's your triple point. On different phase diagrams, you could have, say, 3 solid phases that have the same energy, and that would also give you a triple point. As long as there are 3 phases, same energy, it's a triple point. It doesn't matter if the 3 phases are solid, liquid, gas, all 3 solid, 2 solid and liquid, etc. Triple point just means 3 phases with the same energy. Now, if you have a single compound phase diagram, according to the phase rule, you can never have a point where more than 3 phases have the same energy. And so above the critical temperature, the compound cannot be condensed into a liquid or solid. Again, the region above the critical point is referred to as supercritical fluid. And it's kind of interesting. Supercritical fluids are being studied to try to replace organic solvents. And so organic solvents are not very good for the environment. But if you can use a supercritical fluid that is better for the environment, there are some benefits. So for example, supercritical carbon dioxide can dissolve organic compounds. It's used to remove caffeine from coffee, and it's just CO2. And so it's much better for the environment than many organic solvents are. Now this video is really kind of cool. What we're going to see is that we have a liquid here and a gas, it's gas there, in the sealed container. And so as you raise the temperature, you're also going to raise the pressure because it's a sealed container. And so you go from a region where you have 2 phases to a region where you have just 1 phase, just a supercritical fluid. And then after they form the supercritical fluid, they're going to cool it down, and you'll see the 2 phases come back again. And so they're heating it up, And so again, because it's a silicon system, the pressure is also increasing. And again, remember, where you see liquid, you also have the vapor. And so now we go from two phases to a single phase. And again, that's the supercritical phase. And now, as you cool it down, all of a sudden, you have two phases again. It's really, really kind of cool. And the way of thinking about it is you're starting in that liquid region for the phase diagram. You're heating it, going to the supercritical fluid phase. And then as you cool it, you're going back to the liquid region where you have two phases again. It is really kind of awesome. And again, supercritical fluids may be very important in terms of solvents. And for CO2, the critical temperature is 304, critical pressure is 73 atmospheres. For water, it has a critical temperature of 647 and a critical pressure of 218. And so it's a little bit more difficult to make supercritical water than supercritical CO2, but it's possible. And so is there water on Mars? Now, if there is, what is the form? And so there is water on Mars. We can actually use the phase diagram to understand in what form the water is. And so atmospheric pressure on Mars is 0.7% of that on Earth's. And that tells us there cannot be any liquid on Mars because we're way below that triple point. And so any water on Mars would have to be in the form of ice and the form of gas. And so ice has been detected on the poles, and gaseous water has been detected in the atmosphere. And so the composition atmosphere of Mars is about 95% CO2 and 0.03% water. It's also kind of cool. During the Martian winter, the CO2 from the atmosphere forms solid CO2 on the poles of Mars. And so this video shows you the North Pole of Mars. And so during the winter, you have a lot of solid CO2. That's why it's white. And then during the summer, that CO2 sublimes, going from a solid to a gas. And so that changes back to the orange color. And so because of this, there's a seasonal fluctuation of atmospheric pressure of Mars about between 20 and 30%. So the atmospheric pressure varies by 20 to 30%. Water has also been found on the moon. And again, because the moon has no atmosphere, we're way below the triple point. And so only water on moon should be ice or water vapor. And so ice crystals were actually found on the moon. This is the phase diagram. This is a larger phase diagram of water. And so we're typically down here. Notice that this is millipascals, and so this is very high pressure. And so we never see ice 7 in our daily lives. But it's kind of interesting. It shows us the different phases of water. And the different forms of ice are just different structures. It's also kind of cool if we look at ice 1, because this line goes to the left. Remember, if we increase the pressure, we go from the solid to the liquid. And so that tells us ice 1 is less dense than liquid, but ice 3 is actually more dense than the liquid. Ice 5 more dense than liquid. Ice 6 more dense than liquid. Again, because if we go up in pressure, higher pressure favors the more dense phase. And so ice 6 must be more dense than water. Ice 7 is more dense than ice 6, which is more dense than the water. And so phases and phase transitions can be thought of in terms of a competition between kinetic energy and intermolecular forces. The higher the temperature, the higher the kinetic energy of the particles. And so in solids, you still have motion. You always have motion, even at 0 Kelvin. Again, 0 Kelvin just means the lowest energy states are filled. But you only have vibrations in solids. And then for gases, intermolecular forces are typically negligible, and you just have kinetic energy. And for liquid, you're actually somewhere in between, where the intermolecular forces are strong enough that it holds the liquid together, but the particles can still move relative to one another. I hope that helps.